Hi, this is Kan-Lin speaking. I'm from the National United University Department of Energy Engineering. In this section, we'll talk about the O5. This is the fifth section. We'll talk about linear scanning voltammetry. But this one is different from previous sections 3 or 4. This one, we are talking about the linear scanning voltammetry, LSV, at a faster scanning rate. So in previous section, we talk about is at a slowly scanning rate, but this one with much faster scanning rate. So the phenomenon or the electro phenomenon we measure is at a transient phenomenon and steady state. Instead of previous, we're scanning the electro potential at a very slowly scan. So the data we measure, you might think it's at a steady state, but this one is an unsteady state at a transient phenomenon. So what we see is when at a transient scanning rate, that means at a faster scanning rate, we are talking about scanning rate is greater than 20 millivolt per second. Sometimes even go to the 200 millivolt per second, even higher than that. For the near steady state, the scanning rate is less than 2 millivolt per second. So that's the difference. So the potential will be linear change as a function of time, maybe increase or decrease, doesn't matter, as a linear change. And then you measure the current as a function of potential. You end up with a peak. You might have a peak, a current around here, certainly, and then it will drop, gradually decrease. What happened is that we consider on the left side, the diagram, the concentration profile in the solution. The concentration at the beginning is uniform. There's no electrochemical reaction. The concentration uniform across the entire solution. When at the time we start the electrochemical reaction, then the concentration at the electrode surface will be decreased. And then when electrode become more positive, increase, then concentration at the surface will decrease further, and also the concentration profile will keep changing and penetrate inside the solution. And from C1, C2, C3. When at the C3, the electrode concentration, the concentration at the electrode surface almost go to the zero. This means the electrode current was controlled by the mass transfer condition now. So even you increase potentials, go to a more positive condition, the current will not be increased, instead of decreased, but because it's controlled by the mass transfer limiting current, and that concentration profile will change from C3 to C4 and C5. So you can see the slope from here will be decreased. So you can see from the time 0, the current is 0 at then you go to the time T1, the concentration is C1. There will be the current will be increased to C2, and then to the C3 is a kind of shift from the kinetic mass transfer mixed control region, shift to the mass transfer control region. So the entire process was controlled by how fast the species diffuse onto the electrode. So if you change the potential, become more positive, nothing going to happen because the concentration profile will shift from C3 to C4 and C5, and then slope will gradually level out, decrease. So the current will be decreased like this at the T4 and then the T5. So you end up with a peak behavior like a current against a potential. Instead, at a steady state, you may reach a limiting current that way. So at a fast scanning rate, the linear voltammetry actually the similar. The only difference in mu, the scanning rate is much faster over here. So you end up with the current, you record the current as a function of time. You might end up with the peak. And then you plot the current against the electric potential. You might end up with a peak current here at the peak potential at this location. Similar like a linear scanning voltammetry at a low scanning rate, kind of, but you will not at a low scanning rate. The current will be reach a plateau rather than a peak here. So if you had a potential Over here, we can use a step potential describe the transient behavior of the fast scanning rate LSV. So if we consider the step to the 1 to the step 2, 3, 4, 5, then we record the current against the time. Then you can see at the lower scanning rate, at the lower step potential, the current is a little bit lower. As the potential getting much higher, the current will be increased much higher. But at the potential at the 3, then it may be reached to the mass transfer limiting current. So it's not controlled by the potential anymore. So even if you step the potential to 4 and 5, the current always behaves the same. So if we sample the current at the time 1, then you sample the plot the current against potential at the potential 1, 2, 3, and 4, 5. You end up with this polarization curve. This polarization curve is similar like we do the linear scanning voltammetry at a low polarization scanning rate. So if we sample this current against time at the T2 and T3, what happened? So in that case, the sample at the T1 and T2 and T3, then we end up with the current behavior like this. So the at the T1, the current polarization curve and the T2, T3 will be gradually decreased, something like this. So if I scan it further down, you can see from the T1, T2, T3, and then even the T4 and T5 to the maybe gradually reduced. So this one you can see from here, we plotted the 3-dimensional plot, the current, time, and the voltage here. Previously, if you run a step potential, then the current against time like a green show like a green. If you step at a different potential, if you step at a potential in this region, the potential in this region, then you end up with the current against time. It shows similar. They always behave the same. This at a irreversible mass transfer limiting condition. But if you control the step potential at this region, then it's a kinetic control. So you end up with the current against time will be something like this. It depends on step potential. The current time will be changed. But also you can see from cross section for a given time, then you end up with a current against potential, something like this. At a time, at a very slowly, you get a very large variation. The polarization curve show like this, and as the time get going along, the polarization curve will be decreased like this. But for the linear scanning voltammetry, the potential and the time both are changed, not like a step potential. We keep it at a constant potential, just record the current as a function of time. Both that they are changing. So this one, like we slice this voltage, this contour against the cross section like this, and then the potential against time is like this dashed line, a linear change as a function of time. The potential, just shown by this diagram, you can see. And then the current we measure actually is a cross section for this plane, like a plane cut into the cake diagonally. So the dashed line here will be the recorded current. We call the current against the potential. If you plot the current, this current against the potential, you end up with this. And on the surface, concentration will be changed from this reactance A will be reduced, but the product A- will be diffused out to the surface, from the surface to the bulk.